Good afternoon. My name is Colt Hambury, and today I'm going to be teaching an Introduction to Solar Physics course lecture at the Tambury Institute of Science, course 2112. The title of the lecture is Solar Structure and Heat Transfer, and today we're really just going to be talking about the structure of the sun going from the innermost parts to the outermost, the primary processes which occur in each layer, and some interesting consequences for the Earth-Sun environment, or space environment, I should say. So to begin, we're going to talk about the core, which is where energy is essentially produced in the sun, which then radiates outwards. You'll note that in each of these slides, I have a simple diagram of the sun on the right side. This delineates some layers in the sun. However, it's important to keep in mind that the layers essentially here are blurred. So while we identify particular locations where processes tend to take place, the exact differentiation between these layers is guided more by a slow transition rather than a strict transition. Although these transitions are generally produced by thresholds, for example, temperature thresholds, for example, within which identify when certain processes can take place. So with that, let's talk a little bit about the core. The core of the sun extends from 0 to 0.3 solar radii and is the location of thermonuclear fusion, which produces a significant amount, or the amount of energy which the sun radiates. This process of thermonuclear fusion, as shown in the diagram below, is the conversion of hydrogen into helium and energy. It occurs in the core at about 15 million Kelvin, and in the diagram you can see that essentially hydrogen 1, which is just a proton really, is converted through this process, this three-step process with the first two steps occurring twice for every occurrence of the third step, into helium-4, so an alpha particle, and a certain amount of energy as designated by the gamma rays or the photons as shown in the diagram. Moving outwards to where it's a little bit too cool for thermonuclear fusion to take place, roughly 6 million Kelvin, from 0.3 to 0.6 solar radii, heat transfer is driven in this shell, called the radiation shell or the radiative shell, by radiative diffusion and thermal conduction. Photons travel slowly here, however, because it's so dense in the region. The photons, when they travel from the core to the end of the radiation shell, are essentially absorbed and released or emitted by particles, molecules, and atoms within the radiation shell, so that it takes this kind of drunkard's walk through the region. So they travel slowly, and it takes over 170,000 years on average for a photon to traverse the layer. So although we think of radiation as essentially energy going outwards, which it eventually does, it's a much less direct route than these arrows might suggest. It's more of a sporadic route from the core to the end of the radiation shell. Moving outwards, we then have the convection shell, where heat transfer is driven primarily by convection, with heated plasma ascending in these bubbles and cooled plasma, once they've reached the end of the convection shell, descending. This is allowed by a steep negative temperature gradient, so although we say that the convection shell has a temperature of about 1 million Kelvin, this really changes sharply. And that's what allows the plasma, which is rising, to remain warmer than its surroundings until it reaches the photosphere, releases a lot of energy, and can sink again to the bottom of the convection shell, only to produce the process over and over again. So it's this rising and falling of energy which produces the convection shell. Right outside the convection shell, we have the photosphere. Now, the photosphere is 100 kilometers thick, has a temperature of about 5,800 Kelvin, and is what we generally think of when we refer to the surface of the sun. So it's what you see, the solar disk, what you would see if you could look at the sun. Significant visible features on the photosphere, or the surface of the sun, include sunspots, which are slightly cooler regions of constrained by magnetic energy on the surface of the sun, faculae, and granules. Granules are essentially the visible part of the rising and falling convection cells, which we saw in the last shell. So those are just a few of the structures which can occur. discussion of when these structures occur and the 11-year cycle through which they occur should be left to a future discussion. But it's important to know that these are where these structures potentially exist. In the chromosphere, just outside of the photosphere, extending to between 1,000 to 2,000 kilometers above the surface, the temperature is about 30,000 Kelvin, which you'll notice is actually a bit hotter than the 5,800 Kelvin, which we saw in the photosphere. Visible features here include structures which extend beyond the photosphere, so prominences above the limb, filaments which are seen across the disk, dark streaks across the disk. These two are essentially the same thing, long, big streaks of plasma, but when they occur around the limb of the sun, so on the outside of the disk, they appear bright against the backdrop of the darker sky, and filaments occur slightly darker because they're seen across the disk of the sun. Solar flares also occur in this region, which are very explosive bouts of energy, usually associated with an active region, which tends to be identified by sunspots. Just outside of the chromosphere is the corona. Now, this is really invisible to typical observing. It occurs between 2,000 and 1,000,000 kilometers above the surface, with temperatures of about 1,000,000 Kelvin. You'll notice that this temperature is a return to essentially the temperatures of the convection shell, which suggests a negative temperature gradient, or a positive temperature gradient, I should say, from the photosphere to the corona, and is identified by the coronal heating effect, which is a very mysterious effect within which we see that across the corona there actually is an increase in temperature as we get farther away from the sun, which is a little counterintuitive. A lot of researchers at CU Boulder and other places are spending quite a bit of time on determining the exact reason for this heating effect. The corona is the source, or the driver, I suppose, but the source of solar wind and coronal mass ejections, the latter being explosive ejections of plasma from the sun, and the former being a steady stream, which has some variation, a steady stream of particles from the sun. Both of these structures, when interacting with the Earth and when directed at the Earth, can produce geomagnetic storms, which essentially is a large influx of plasma into the magnetic field of the Earth, producing structures such as the Aurora Borealis or Australis, and in some extreme cases, even blackouts. The corona is visible during a solar eclipse when the photosphere is blacked out by the moon, as you can see in this picture of the August 21st solar eclipse from a few summers ago, 2017. But this method is artificially produced by lots of cameras, usually space-bound satellite cameras, which can image the corona and observe these large ejections of energy called coronal mass ejections by just blocking out the disk of the sun and being able to see the corona. So that's the general structure of the sun as we know it. It's paralleled quite a bit by a number of other stars, but of course this depends on the exact point in the star's life cycle. There are lots of different mysteries still to figure out about the structure of the sun, even the most basic parts of the structure of the sun, and there's lots of work to be done, which is being done with an increasing amount of attention. Thank you.